In this problem, we are given several, actually 4 graphs, and we are supposed to assign each of the graphs one of the letters for the different function equations to match each one with the correct graph. And what we might notice first is that these are all rational functions, and all of these rational functions have a vertical asymptote of 1. How we would know that is to set the denominator equal to 0, since we know we cannot divide by 0. And if you were to set x minus 1 equal to 0 and solve for x, you would get x equals 1. And notice that when you plug 1 into where the x is in the denominator, that denominator would become 0. So that indicates that the function should not be defined when x equals 1. So if you look at this first graph here, you can see that when you go along the line, the vertical line where x equals 1, you do not see the graph defined along that line. And all of these graphs have that in common, and all of these equations have that in common. So we're not going to get any help differentiating between these to match them up with the different pictures by focusing on the vertical asymptote. We can look at horizontal asymptotes, and recalling that horizontal asymptotes there are several cases. There are actually 3 cases when it comes to non-vertical asymptotes. You can have a horizontal asymptote on the x-axis, and that occurs when your function is what I call bottom heavy. So like option C here, notice that the degree of option C is greater than the degree of the numerator. So I meant to say the degree of the denominator in option C is greater than the degree of the numerator. So that would indicate that the top is going to be increasing much more slowly than the bottom, and in fact the bottom will be increasing exponentially faster, and so this is going to eventually approach 0 as those numbers get huge, the x values. So C should have a horizontal asymptote at y equals 0, the x-axis. So let's look and see if any of these examples here look like they have a horizontal asymptote at the x-axis. Well, the thing about horizontal asymptotes is that they're kind of tricky. And you might have noticed I already have the letters assigned to each of these, so it's a giveaway. They're actually in order A, B, C, D. I don't know if that's going to be the case on all of these versions of this problem, but right now that's how they align. And so we can see, excuse me, knowing that C goes along with this third option, we might look at that and say, well, look, it's supposed to have a horizontal asymptote on the x-axis, but the function is actually going through and over the x-axis. And that's not necessarily an indication that there is no horizontal asymptote. With vertical asymptotes, the function can definitely not ever cross that vertical line. But when it comes to horizontal asymptotes, the definition is actually different, and this is more focused on what the ends are doing close to that line. So you'll notice that on the x-axis, the horizontal asymptote, according to the equation, if you look at the ends on the right, you see that this function is hugging very close to that x-axis there. And also on the other end, you see the same thing happening. So with horizontal asymptotes, you really want to focus on whether the ends are aligning alongside the horizontal line um, and not touching it, right? So just kind of running very close to it, but not crossing it. Anything else can happen in between those ends, and that's okay when it comes to horizontal asymptotes, but you want to really focus on what the ends are doing. Okay, so vertical asymptotes cannot be crossed. Horizontal asymptotes can be crossed, and you want to focus on what the ends are doing, that if they look asymptotic, if you see asymptotic behavior close to that line at the ends. So I do see that it appears that we do have that horizontal asymptote there, and so C would have been a good choice to match up with option C, or the third picture matches with option C. The fourth option here, option D, the equation shows the top of the fraction, the numerator, has a higher degree, one higher exactly, because the degree on the top is 2 and the degree on the bottom is 1. We're looking at the exponents of x. So what we see is that with a top-heavy rational function where the degree of the top is exactly 1 greater than the degree of the bottom, then there is no horizontal asymptote actually. Instead, there is a slant asymptote, or also known as an oblique asymptote. And we would find that by doing the division and disregarding the remainder. And since this is a linear denominator, meaning that it's to the power of 1, x is to the power of 1, degree 1, polynomial denominator, we can use synthetic division to find that slant asymptote equation that would be in the form of y equals mx plus b. Now I can look at the end behaviors of each one of these graphs and see that this one appears to have the ends close to y equals 1. So I wouldn't look at that one for option D. I'm looking for the one that appears to have no horizontal asymptote and instead a slant asymptote. Well, notice that here, this option D here, this one, the ends do not get close to the same horizontal line. You would want to see that your two ends, that all your ends are, you're going to see one end on each side at least, hugging very close to a certain horizontal line and the same horizontal line. And we don't see that at all, right? So we don't see any of these ends of this function hugging close to the same horizontal line. So this one shows no horizontal asymptote. Also, we can visualize a slanted line between the two pieces here, and that looks like a slant or an oblique asymptote. Okay, so that one definitely matches along with D without us even looking to find out what the equation of that slant asymptote is. All right, so we have the top one, remember, had actually, I don't think we talked about the horizontal asymptotes of these two. We just talked about the last two down here. And I'm not quite sure why I skipped to these two. I guess because they're a little more interesting. These two up here have the same type of horizontal asymptote. And they're both, the same degree on top and bottom. So this one is degree 1 on top and degree 1 on the bottom. So they're going to have an asymptote at y equals the ratio of the lead coefficients. So that would be y equals 1 over 1, or just y equals 1. So you can see that there's a horizontal asymptote at y equals 1, so that matches with that. Same thing's going to happen for b. We should see that the powers or the degrees on both of the numerator and the denominator in option B are the same, so they should have a horizontal asymptote that is equal to y equals with the coefficients of lead coefficients on top and bottom over each other. And so that would equal 1 here because again, the x's are just going to have a coefficient of 1 when you multiply everything out. So both A and B have a horizontal asymptote of 1. And notice that option B, if you draw a horizontal line through x equals 1, what you see is that the ends are kind of look like they're getting closer to positive 1, the line of 1. As x goes towards positive infinity, you see the end approaching that horizontal line. And as x approaches negative infinity, you see the function also approaching that line. So this one appears to have a horizontal asymptote of 1 as well. So then how did we know if A is matched to that first one or not, and if B is matched to that second one or not? So we have to think about it a little deeper, since both of these have the same vertical asymptote and the same horizontal asymptote. So how are we going to differentiate between them? Well, one of the things I'd like you to notice is that the denominator of A has a degree 1, and odd degrees usually result in a shape that's more like this, where the parts are on opposite corners of the plane. And then B, option B, has a denominator of degree 2, and even degree denominators usually result in a function that has a couple of the ends pointed in the same direction on the same side of the x-axis. So, and I tend to call them that they look like volcanoes, kind of like a volcano or an upside down volcano. So these two in the middle should have denominators that have an even degree on them. And so notice that B has that even degree, as I just pointed out, and then C has an even degree as well. So it makes sense that those two middle ones are looking like volcanoes. Another way to tell is just to when we're looking at A and B and comparing them and saying, well, they have the same asymptotes, so how do we tell the difference? If you didn't realize that the volcano shape kind of gave it away, that B was matched with the second picture, if you didn't think about that and you didn't realize that, you could also just inspect both of them, visually inspect both of the pictures, and look for something that's different between them. So notice they both go through the x-axis at x equals 2, right? So that doesn't help anything. But what about the y-intercept? So the y-intercept for the second option is right through 4, and the y-intercept for the first option was through y equals 2. So I could simply use that point, one of those points, in either one of these equations and see if I get a match. Because any point that is on a function has to make the equation true. The equation that goes with that function has to be true when you plug in a set of coordinates that is lying on that graph. So I could say, well, I think A might go with the first picture. So I'm going to take that y-intercept of 0, 2, and then I will replace the y with 2 and then put zeros in for the x's. And so what you'll notice is that on the right side, when I put zeros in for the x's, they will disappear essentially, and you will be left with -2 divided by -1, which equals +2. And that is the y value that you should get when you put zeros in for x. So this option A is aligning with that first picture. Now I'm extremely confident that that is the right choice and that B would have to go along with the second picture.